Hey everybody, it's Mrs. Cassell. Sorry for the delay in these. I was sick the first week of break, so I'm recording these at home. So they'll look a little different than when I do it on the document camera. It's cool. So, number 10. A carton shown in the diagram to the right lies in a plane tilted at an angle of theta equals 22 degrees from the horizontal with a coefficient of kinetic friction equal to 0.12. So, part A, determine the acceleration of the carton as it slides down the plane. So, the acceleration of this carton is going to be the result of the net force acting on this object. So, you can see that they've already suggested a vertical y and a horizontal x that's parallel and perpendicular, respectively, to the surfaces of the ramp. So, I'm going to draw my forces over here on the diagram first, and then I'll draw my real free body diagram. I'm going to have the force of gravity acting straight down towards the bottom of my page. I know that there's some force of friction because of this coefficient of friction of 0.12 that's going to be opposing that sliding motion. I'm going to have some normal force right there, and this object is just sliding. There's no other forces. The other thing that I'm going to want to consider here is going to be thinking about this angle, theta, right here. I know, because I can think about some similar triangles and some alternate interior angles here, that if this is 22 degrees right here, then this angle right here is going to be theta minus, or 90 minus theta, so it's going to be 90 minus 22 degrees. And I'm thinking about what's this angle right in here, where I've made a little blue mark right there. Call it our angle phi if you want. So if I think about my alternate interior angles, well, if this is 90 minus theta and this is 90 degrees right here, well then that phi right there, that's actually not phi, it's theta, it's 22 degrees. So when I draw my free body diagram over here, where I've tilted my paper to make it have y in the vertical direction and x in the horizontal direction, I've got my force normal acting upward, my force of friction off to the left, and I've got the force of gravity acting right down here, and this angle right here is going to be the same as the angle on our ramp. It's going to be theta. It's going to be 22 degrees. Okay? So, first step of doing any net force problem is drawing our free body diagram. Second thing we're going to do is we're going to break our forces into components. If I want to end up with only vertical forces and horizontal forces, we're going to find out using this triangle right here, what are those, the vertical component in the of the force of gravity, and what's the horizontal component of the force of gravity. Okay, so I'm going to draw a triangle here, thinking about that we've got a force of gravity as our hypotenuse. We've got one side that's our vertical component, and we've got our other side that's our horizontal component. Our angle theta is right here, and this is a right triangle. So when I think about this, I'm going to solve for my different sides of my triangle. I'm just using my normal Pythagorean theorem, or you can use, well, I guess we can't use Pythagorean theorem yet. So I'm going to go ahead and erase that because I don't have a lot of room for that on this little app. So, okay, so if I'm going to find my vertical component, it's going to be equal to my hypotenuse times, this is my adjacent side, so it's going to be the cosine of my angle, and my horizontal side, which I guess technically should have been green, right? I mean, I'm going to follow the rules. I should follow the rules, right? It's equal to my hypotenuse, which is the force of gravity, times its opposite side, sine of theta. So those are going to be numbers, right? Except I don't know the mass of my box, so I'm going to leave them written like that for right now. I'm going to redraw my free body diagram then, thinking about labeling these two forces right here. So, I'm going to erase that right there. So now my forces look like this. In the x direction, I've got force of gravity times the sine of theta. And in the y direction, I've got the force of gravity times the cosine of theta. So now, my next step is I can sum my forces in the x direction and in the y direction. You can think about a couple things. First, the vertical direction is important for us. So the net force in the y direction is going to be equal to my normal force plus the force of gravity times the cosine of theta, because those are my two forces here in the vertical direction. So the other thing I know about this is there's no acceleration in that direction. So that's going to be equal to 0 newtons, and I'm going to use that a little bit later here. Net force in the x direction is going to be force of friction plus force of gravity times the sine of theta. And that's going to be equal to my box's unknown mass times that acceleration that I'm looking for, right? This is the acceleration I'm trying to solve for right there. So, a couple things that will be useful to us here is that I'm going to have my mass times my acceleration equals the force of friction plus the force of gravity times the sine of theta. And when I think about what my force of friction is, right, that's going to be my coefficient of kinetic friction times my normal force plus my force of gravity times the sine of theta. So that means that I can take this equation up here and I can solve this for the normal force. That's one of the things that I'm going to want to do. So if you do your algebra for that, you get force normal equals negative force of gravity cosine of theta, if I'm checking if my fingers are right. So now I'll do one more substitution here, which is, you know that whenever you see force of gravity, that's equal to the mass of an object times the acceleration of gravity. So when I rewrite my net force equation right here, this one that I'm talking about, I'm going to have mass times acceleration is equal to the coefficient of kinetic friction times the force of gravity times cosine of theta. Oh, hang on. I should have done this, right? Whoop. Should have done mg cosine of theta plus mg sine of theta. If I paid attention, you'll notice we've got m cancels everywhere. So now we have an equation that's just a number. Acceleration is going to be equal to our negative coefficient of kinetic friction times the acceleration of gravity becomes a cosine of 22 degrees, because that's our angle, plus the acceleration of gravity times the sine of 22 degrees. Okay? So, and really, that little parenthesis right there is going to annoy me, and I'll just erase everything in the process. So, you guys must get so tired of the sound of my voice. I just gotta tell you, I admire you all. So, I'm going to plug that into my calculator. Alright, when I plug all that in my calculator, I get 2.58, and this is the acceleration, meters per second squared. Alright. Now, remember how we turned our paper sideways? That's still going to help us when we think about part B right here. We now have an object. For all we know, it's propelled by rocket boosters, and it has an acceleration of 2.58 meters per second squared in this direction. So when we're given this scenario, imagine this is a race instead. We've got our rocket-powered box that starts from rest and travels a distance of 9.3 meters. And we want to know what is the speed when it reaches the finish line right here. So when we get to our finish line, how fast is it going? That's the only thing that we have to figure out. So this now is just a kinematics problem. So I'm going to look at my kinematics equations. I'm going to decide that, well, my initial velocity is at rest, and I know my acceleration, and I know my displacement here, that I can solve for my final velocity. What is this, from my finger right here? Good grief, okay. So, where did my thing go? Right there. So, that's the rearrangement of my equation. So my final velocity is going to be equal to 0 meters per second squared plus 2 times my 2.58 meters per second squared acceleration times my displacement of 9.3 meters, and then I'm going to do all that, and I'm going to take the square root of that. So in my calculator, it equals 6.93, and that's going to be meters per second. So